In this video, we're going to discuss two quantities deeply related to energy. They are the Helmholtz free energy, given by F equals U minus Ts, where T is the temperature and S is the entropy, and the Gibbs free energy, which is the energy plus PV, which also looks like the enthalpy, and then we again subtract this Ts term. Now, just like energy and enthalpy, we're not really going to worry about the total value of the Gibbs free energy or the Helmholtz free energy for most systems. What's going to be most interesting to us is how these quantities change as some reaction happens. Let's begin by talking about the change in the Helmholtz free energy. So the change in the Helmholtz free energy as some process occurs looks like the change in the energy. And then here we've just used the product rule. So we have T, temperature, multiplied by the change in entropy, minus the change in the temperature multiplied by the entropy. And what we're going to do is we are going to assume that the temperature is constant, because it turns out that the Helmholtz free energy is most useful when we assume constant temperature. This is very similar to what we did with the enthalpy, where we considered that the products or the reactants and the products ended up at the same temperature in the end, and we measured our changes in enthalpy with a constant temperature as well. Okay, so let's see why this turns out to be a very nice assumption to make, that we have a constant temperature. Well, if we expand our change in energy, we know that our change in energy is simply the heat plus the work done on the system. But we also know that for a quasi-static process, that is a process that happens slowly enough that all of our kind of descriptions, variables for the system remain well-defined, volume, pressure, etc. remain well-defined. As long as that happens, our heat added to the system is equal to the temperature times the change in entropy of the system. So if heat enters the system, well, then I can tell you how much the entropy of the system changed. And if heat leaves the system, I can also tell you how much the entropy of the system changed. So with this, we can cancel out the Q and T delta S terms, and that leaves us with an equation for delta F, the change in the free energy, the Helmholtz free energy, as being equal to the work. So for a quasi-static process at constant temperature, the change in the Helmholtz free energy of the system is equal to the work that that system can do. So this work includes both compression work and other types of work, such as electrical work. Now let's go through the same process for the change in the Gibbs free energy. The Gibbs free energy is U plus P times V minus T times S. When we want to find the difference in it, we again can use the product rule to write out the, say, dP times V, P dV, etc. And what we're going to do here is we're going to assume constant pressure and constant temperature. Constant temperature, again, turns out to be very useful, and constant pressure is actually very useful because many experiments are done in a lab exposed to the atmospheric pressure, and so the pressure for many experiments is just constant. And it turns out that when we use the Gibbs free energy with constant pressure, we can find out about work as well, just like we did for the Helmholtz free energy. Okay, so these two terms are going to be zero because our pressure and temperature aren't changing, which means we can rewrite our Gibbs free energy as this. Now we're going to use the same trick that we did with the Helmholtz free energy, where we write out delta U in terms of the heat and the work. But now what we're going to do is we're actually going to split our work into two different types. We're going to have the compression work, and we're going to have the other work. So this includes something like electrical work, right? Okay, so if we want that to happen, well, we know that our compression work is negative P delta V, and we know that our heat is T delta S. Both of these are true for quasi-static processes, but that's what we're going to be considering here is quasi-static processes, so we can use these equalities here. Okay, so plugging these equations in here, we see that the Q cancels with the T delta S, And the compression work or expansion work cancels with the P delta V. So our change in the Gibbs free energy is actually just the amount of other work that the system can do throughout a reaction. So for a quasi-static process at constant pressure and constant temperature, the change in the Gibbs free energy for that reaction is equal to the amount of other work that that reaction can do. Now, to make better sense of what this really means, let's look at a specific example. To get a better sense of what the Gibbs free energy means, let's take a look at a specific example of combining hydrogen and oxygen to make water. So we're burning hydrogen and oxygen to make water. Okay, so first the reaction starts in a gas form here, and we end up with water in liquid form. Now, if you think back to our discussion of enthalpy, the enthalpy of a reaction is the amount of energy that comes from the reactants themselves bonding, the bonds between the atoms forming, which releases energy, and the atmosphere collapsing as the system shrinks from a gas form to a liquid form. So the change in enthalpy of the system is basically the sum of those two energies. And in this case, we have a gas going to a liquid. We have a release of energy from the molecules as they bond together. And we have energy being added into the system as it is collapsed. Now, just like with enthalpy, in Gibbs free energy calculations, we are going to assume that the temperature of the system is the same before and after, which means that all of this energy, this delta H from my two sources, my chemical energy and my collapsing atmosphere work energy, must leave the system. This is why my delta H is negative, because I cannot let the system heat up. That is my definition of how I am measuring my enthalpy, is that my temperature is the same before and after, which means that all of this energy that the system has created by forming these bonds and releasing energy and the atmosphere collapsing must be released. That's why my delta H is negative. So the system has to get rid of 286 kilojoules of energy, assuming that I did the reaction with 1 mole of hydrogen, 1/2 a mole of oxygen, and then 1 mole, creating 1 full mole of water. This is the amount of energy I need to get rid of. Now, in the enthalpy discussion, we assumed that all of that energy needed to leave in the form of heat. So it just goes and it heats up the environment, which is possible, but it doesn't have to leave the system as heat. And in fact, it can leave the system as useful work. And what the Gibbs free energy is going to tell us is what portion of this energy can leave the system as useful work and what has to be released as heat to the environment so that we don't violate the second law of thermodynamics. Okay, so why do we have to give off some amount of heat at all? Why couldn't we use all of this energy to do some kind of useful work? Well, the answer is that we have to make sure that the entropy of the full universe does not decrease. But when this reaction happens, I have gases going to a liquid. Liquids have lower entropy than gases. So I am actually losing entropy in my system here as this reaction occurs. How much? Well, I just looked it up in the back of the book, and for 1 mole of hydrogen, 1/2 a mole of oxygen, and 1 mole of water, the reaction loses me 163 joules per Kelvin of entropy. So this H2O has less entropy than we started with. Now, we cannot let the total entropy of the universe decrease, which means we must increase entropy somewhere else. Where can we increase entropy? In the environment around my system. So the idea is that we release some of this enthalpy energy that we have stored. We have 286 kilojoules that we can get rid of in some form, and we can dump some of that into the environment and increase the entropy of the environment. How much do we need to dump? Well, we need to make up for this amount of lost entropy. And so what we can do is we can dump T times delta S into the environment, right? So the idea is that we need the environment to have an increase of entropy of delta S equals 163 joules per Kelvin, right? If we want to do that, we need to dump some amount of heat into the environment. How do we find out how much? Well, we just use our handy relationship between delta S and heat. And so the amount of heat that we end up needing to dump into the environment is just T times delta S. So T here refers to the temperature of the environment, though in this reaction we are assuming that we are keeping the system and the environment at the same temperature at all times, so there's only one temperature here. Since the table in the back of the book only deals with 298 Kelvin, that is the only temperature we can use when doing these types of Gibbs free energy calculations. Okay, so we need to get rid of this amount of heat so that we increase the entropy of the environment by at least as much as we decreased the entropy of our system when our reaction happened. So, in the end, the amount of energy that we can get out as useful work is the enthalpy, the total amount of energy that we need to get rid of so that the temperature of our system doesn't increase through this reaction, minus the amount of energy that we need to dump into the environment in order to not increase or not decrease the entropy of the universe as a whole. So in this case, that is 286 kilojoules that I need to get rid of, 49 kilojoules, which is simply my 298 Kelvin multiplied by this number here. Notice that this is in joules and this is in kilojoules. So when you multiply these together, you're going to get 49,000 joules. So we have negative 286 for my enthalpy. I end up adding 49 kilojoules onto that for the amount of heat that I need to get rid of it to the environment, and I end up with negative 237 kilojoules. Again, remember the minus sign means that the system is giving this energy off. So there are 237 kilojoules of energy that I can give off through this reaction as useful work, and the other 49 kilojoules has to be given as heat to the environment. As a final thought on this example, I just want to remind us that this 237 kilojoules that will be given off cannot come out as compression or expansion work because we have already assumed that the system compressed by a certain amount as it went from its gas state to its liquid state. So in using the enthalpy, we have already taken into account the work done on the system as it collapsed. So this amount of work that we can get out must come in the form of some other type of work, probably something like electrical work, that is moving electrons through a circuit, for example. Now let's look at one final useful property of free energy. We're going to look specifically at the Helmholtz free energy, though you can do a very similar calculation to show that the Gibbs free energy has a similar relationship to entropy. So here we're going to look at the Helmholtz free energy and its relationship to the change in total entropy of the universe. So this is the entropy of the system and the entropy of the environment, which we're calling here the reservoir, combined. So the idea is that we have some system, maybe it's some gas that we are trying to keep track of, and then we have the reservoir outside of it, and the system can trade heat and energy back and forth with the reservoir. What we want to do is we want to see how the change in the free energy of the system relates to the change in the total entropy of the system and the environment as we trade energy back and forth. So if we look at just the reservoir, we can write the entropy of it using our thermodynamic identity as 1 over T du for the reservoir plus P over T dV plus U over T dN. Now, for this calculation, we are going to assume that the number of particles and the volume is constant, which means that these two terms are simply zero. Okay, so that means that the change in entropy of the system, or of the reservoir, is just equal to the change in energy of the reservoir divided by the temperature of the reservoir. Okay, so plugging that in here, we see that the change in the total entropy is equal to the change in entropy of the system plus this factor here. Now, the useful thing to note is that energy that is gained by the reservoir is the same as the energy that is lost by the system, right? So that means that du for the reservoir equals negative du for the system, right? If my system gives a little energy to the reservoir, the system loses du of energy, the reservoir gains du of energy. Because we are assuming that the reservoir and the system are at the same temperature, they're in thermal equilibrium, we can replace the temperature of the reservoir with the temperature of the system here, since those are the same temperature, whatever that happens to be. Okay, now all we have to do is we just pull out a 1 over T here, and we see that the total change in entropy of the universe, that is the system and the reservoir together, must be equal to 1 over T negative du minus TdS, but this here is just the change in the free energy, right? Assuming that we are at constant temperature, constant volume, and constant number of particles, which is just what we assumed here. And we know that when we were talking about the free energy before, when we used this equation for the change in the free energy, we had already assumed that our temperature was constant. So this equation only holds as long as we have these three variables held constant. But if it does, which is the cases that we'll be looking at, the change in entropy of the universe as a whole is simply equal to negative 1 over temperature multiplied by the change in the free energy. So what this means is that if a system goes through some process in which its free energy decreases, if the dF is negative, then negative 1 over T dF will be positive, and that will lead to a positive change in total entropy for the universe. Now, that means that a process that has a negative change in free energy with these variables, T, V, and N held constant, will happen spontaneously because it will increase the entropy of the entire universe. So, for example, if I have some gases that could react with one another, they will react with one another if the change in free energy for that system is less than 0. That means their reaction will increase the total entropy of the universe. Now let's quickly review what we have learned about the Helmholtz free energy. So first, we found that the change in the Helmholtz free energy is equal to the work done on the system. So if my change in free energy is negative, that means that negative work was done on the system, which means that the system itself must have done positive work, right? The work done on the system is equal to the negative of the work done by the system. So a negative value of delta F for some process means that the system was doing positive work. Likewise, a positive value of delta F for a system or a process means that positive work needed to be done on the system in order to complete that process. Again, this is true for quasi-static processes, and in deriving this, we held the temperature constant. So this is something that holds if the temperature is constant. Okay, we also found that if delta F is less than 0, this means that the process will happen spontaneously for a constant temperature, volume, and number of particles. So if we just look at the delta F for some process, if we know the sign of delta F at constant temperature, volume, and number of particles, we know whether that process will happen spontaneously or not. And finally, let's review what we learned about the Gibbs free energy. So the change in the Gibbs free energy is equal to the amount of work that was not compression or expansion work that was done on the system. So delta G equals the amount of other work that was done on the system during some process. Again, if delta G is negative, that means that the positive work was done by the system there. Okay, this is true for quasi-static processes, and it gives the amount of other work that can be done by some reaction or some process at constant temperature and pressure. So when moving from Helmholtz to Gibbs, we have to hold not only temperature but also pressure constant for this equation. Okay, so we also know that if the change in the Gibbs free energy is less than 0, this means that the reaction is spontaneous. Unlike for the Helmholtz free energy where it was constant temperature, volume, and pressure, temperature, volume, and number of particles, this is true at constant temperature, pressure, and number of particles, which actually makes the Gibbs free energy more useful because most experiments in the lab would be done with constant atmospheric pressure. They would be exposed to the atmosphere. So we can just look at the sign of the Gibbs free energy for some process and see if that process will be spontaneous.